With numerous component scheme options, choosing the right ones can be challenging. Here are a few general guidelines to help simplify the decision-making process. When designing hybrid key exchange systems, it's crucial to choose schemes with independent strengths and weaknesses. The independent strengths of each component are vital because the hybrid key inherits their security guarantees. Equally important are independent weaknesses, as they help mitigate, or ideally eliminate, the risk of a single point of failure. To secure communications during the transition period from legacy to quantum secure systems, it's important to include at least one scheme that has long-standing security against near-term attacks and comes with mature, well-tested implementations. Including a legacy scheme provides stability and reliability in the short term, providing protection against classical, cryptographic, or otherwise threats while transitioning to quantum-resistant solutions. For long-term security, it's also essential to include at least one scheme that's considered quantum secure, such as PQC, QKD, or QSC. Once legacy schemes become obsolete due to advances in quantum computing, they'll be phased out of future hybrid systems. Continuing to use legacy systems at that point would only consume computational resources without offering additional security. However, hybrid key exchange isn't just a temporary solution. It can, for example, combine PQC schemes with QKD and/or QSC schemes to offer enhanced protection against both current and future classical and quantum threats. Individual algorithms and protocols within each key exchange methodology also come with their own unique strengths and weaknesses, giving us added flexibility in tailoring hybrid solutions, but also adding complexity to this decision-making process. Choosing the right component scheme is only part of the process. We also need to carefully consider how to combine them effectively. By appropriately combining our keys, we can ensure that the composite key remains secure as long as at least one of the component keys is secure. Concatenation, XOR, key derivation functions or KDFs, and combinations of these methods are four of the most common ways to combine cryptographic keys. Concatenation joins multiple keys by placing them one after the other to form a larger composite key. It's important to ensure that the resulting key can interoperate with the rest of the security system, especially since certain schemes may require keys of specific lengths. XOR, or exclusive OR, is a bitwise operation where corresponding bits of two keys are compared. If the bits differ, the result is 1. If they're the same, the result is 0. XOR requires the input keys to be of the same length, so careful attention to key length compatibility is necessary for this method. Key derivation functions, or KDFs, are cryptographic algorithms that take one or more input keys and apply a function, typically involving hashing, salting, or other techniques, to generate a new key. KDFs are used to ensure that the derived key meets both security and formatting requirements for cryptographic operations. Multiple key combination methods can also be employed, such as using KDFs in conjunction with concatenation or XOR to address key formatting issues. For instance, a large composite key formed by concatenation can be fed into a KDF to ensure the resulting key is the correct length for symmetric encryption. Similarly, KDFs can be used to format keys before applying XOR to ensure both keys are of the same length. It's important to note that while KDFs can be used to combine keys, they are also commonly applied to keys derived from single algorithm key exchange protocols. In these cases, KDFs are used to provide both added security and ensure proper formatting. Practical considerations beyond just security also influence the component schemes we choose and how we choose to combine them.